Good morning. I'm Toby Schneider. I'm representing my business GobiSoft in Massachusetts, United States. I'm presenting this along with my colleagues Supin and Henrik at the MIT Institute of Technology. My talk is fast, cheap, and good. It's about the development of a high-performance communication navigation system for Arctic deployments using a so-called virtual ocean. A bit of background, we took a Bluefin 21-inch AUV up to the Beaufort Sea at about 71 degrees north in March of 2020 under the sea ice cover. The vehicle was equipped with a number of sensors, the ones that are key for this, an INS, DVL, and a micromodem for acoustic comms. We had a variety of scientific and engineering goals that we were performing as part of the US Navy's ISEX 2020 temporary ice camp. And the development approach we took for this is what I'm calling fast, cheap, and good, taking the cliche and saying, well, we can actually have all three. And this sort of is captured in the fact that we only had a single in-water engineering test prior to the experiment, but hundreds of hours of virtual experiments. So a small, largely student and postdoc-led team, and we took advantage of a multidisciplinary application of simulation tools that I collectively refer to as a virtual ocean, and built on a long lineage of open source software. And I'm going to play this video. You'll hear Henrik talking, give you a little bit of an introduction into the project and some context.
The equipment has already arrived. It's shipped out there before we get there. They have made this hole in the ice. It's a 15 by 3 feet hole. That's where we're going to deploy our underwater vehicle. When you're trying to understand a phenomenon such as the oceanography in the Arctic, you have to map the properties of the ocean, temperature, salinity, currents, in different points in space and in different points in time. That allows us to assess what is the dynamics, how are things moving around, what are the laws driving these changes in the ocean environment. Now, to do that, we need accurate measurements, and we need to know where the measurements are made. And the way we do that is by deploying an underwater vehicle, and it operates on its own. We can communicate with it, but how do we know where it is? When you are below the ice, when you're in the water, there's no GPS. So what we are trying to do at MIT is develop technology that gives the equivalent of GPS accuracy for navigation under the ice. And we do that with basically 3 components. One is a device that is measuring the motion relative to the ice. The second one is the underwater vehicle is transmitting a sound impulse out into the ocean. And that is received by 4 receivers hanging from the ice. When we look at the relative travel times from the vehicle to these various receivers, we can make a computation of where the vehicle actually was when it sent the message. We let the vehicle include in the message where it thinks it was. We compute the actual location, take the difference between the two, and send it back down. Together with information about how much the ice is currently moving, because we are measuring the relative motion to the ice. The third component is understanding the environment. So what we are doing is we're using our measurement of salinity, temperature, to identify where we should be in the water column to get the best possible navigation information. And by putting those together, we can get very accurate navigation solutions.
So that gives you a bit of background as what we were doing. I'm going to discuss now. I think the challenges that we faced in the Arctic are as much logistical as they are technical. As many of you may be familiar with, already working in high latitude regions. The logistics come down to high cost, poor weather, moving ice. In the case of our ice camp, we had a short time at camp. It was scheduled about 5 days, and it turned out to be about 3 due to weather. It was a fixed deployment window. In this case, it's the early spring, while there was sufficient ice cover still to do this camp. And then from the technical side, we had ice cover, navigation, comms, recovery issues related to the fact that we're deploying under ice. And our solution sort of centered around 2 key technical components: the sort of integrated communications and navigation system that we developed, the ICNN, which you could think of a little bit as LVL with data, and then the hydrodynamic model-aided navigation, or HydroMan component, which tied together all the navigation components into one. So this virtual ocean approach that this talk centers around is that given the sort of extreme logistical challenges we faced, we didn't have opportunities to test under the ice. So our approach relied heavily on simulation. And about 5 components here. A communication simulator, which covers the acoustic communications, also called NetSim. Environmental simulator, which covers the oceanographic environment. Topside simulator, which is the operator base station side. A vehicle simulator, which is the vehicle moving through underwater space. And then the last piece is sort of ties this all together, the hardware interface emulation. Rather than just simulating the physics involved, we also want to emulate the actual hardware interfaces, the serial protocols, TCP protocols, etc., so that when we go to deploy this thing, we've minimized as many chances for integration errors as possible. And simulation is a tough tool to use well. It's kind of, as I see it, a balancing act between fidelity and feasibility. How high quality your system is, how easy it is to actually use, create, and manage. So given this approach graphically, basically we put as much code as we can into these 2 boxes for the top side and the AUV, which is shared between the virtual world and the real world. And then all these lines represent the interfaces that connect the real code that we're running on the 2 components with either the simulated world, the simulated sensors, the simulated environment, or the real world. And the goal is wherever possible to make these links look the same as they do on one side as the other, so that when we go put the thing in the water, it acts the same as it does in the simulator, more or less. So making effective simulators is challenging, and I think this is sort of captured because too often simulation suffers either because it doesn't capture the salient challenges of the real environment, it's not good enough, so that your system ends up working in simulation, it works in simulation, but not in the real world, because we're making too many simplifying assumptions. Or it's too complex, computational intensive, or requires specialty hardware, which makes the simulations hard to run. Integrations of the subsystems with the simulator are challenging, and a lot of subsystem developers aren't comfortable running the entire system, so it doesn't get run very much, and thus you don't get a lot in the way of end-to-end testing. And proposed solution to that, sort of which got applied here in this project, is a hierarchical approach of providing essentially 2 simulators, one of which is a low fidelity, but tries to capture the salient features that are necessary. And this is used for everyday development. So you want to target a high ease of use so that people actually use the system. And then a high fidelity one, which inherently includes more complexity. And this can be applied at what I'm dubbing virtual experiments, where you get the whole team together to run a single test kind of end to end, as if you were actually in the real experiment, but all in simulation. And I'd like to point out that I think a low fidelity simulator is much better than none at all, or one that no one runs, which is about the same as not having one. So don't let the perfect be the enemy of good here. Having low quality simulators can be useful for developing and can get you to where you need to be faster. And the last piece I'd say is don't mix simulation and runtime components whenever possible. And this is often done by splitting the simulator and the runtime piece across a certain physical interface, or an interface between a simulated sensor and a real sensor, which could be TCP, serial, or whatever. So that when you're running this in the real world, you're running the same code as much as possible, and you don't have some complex decoupling of your components when you go to put it in the real environment. So I'm going to use the integration, communication, and navigation subsystem, which was my piece, as an example of how we use this approach, effective simulation. So this ICNN is basically broken into 2 components. You got the AUV side and the top side. The hardware was a micromodem attached to the AUV and 4 ice buoys, each of which had a micromodem and GPS attached to it, with 4 receive elements, 2 in the shallow channel at 30 meters, and 2 in the deep channel about 90 meters. And each alternating buoy had a transmitter at the shallow or deep channel. So we could choose between which depth we transmitted at, as well as which depths we received at. So the vehicle transmits a packet at a synchronized time based on an onboard atomic clock. These are picked up by the buoys, which provides us with a travel time, which goes into multilateration of the position so you can estimate where the vehicle is, send that correction back down to the vehicle on the next packet, which is sent over to navigation to update the navigation solution. In addition to that, we ran a bit of onboard simulation on the top side to detect or to estimate which of the 4 transmitters would be optimal for increasing the probability of reception for messages sent to the vehicle. So when developing this simulator, there's a couple of key oceanographic features we want to capture, one of which is that this so-called Beaufort lens. So the climate change is dramatically modifying the Beaufort Sea sound speed profile due to a warm water layer. So as you can see in this sound speed profile on the left, the solid line is the present day profile, and the dashed line is a historical profile. And so the historical profile is largely monotonically increasing, whereas there's a significant lens in this modern profile. And so when they look at acoustic propagation from a source at 30 meters in both the old and the modern day profiles, the old profile you see relatively decent coverage over a sort of evaporation region, whereas in the new profile is a very pronounced shadow zone, as well as a more distinct surface channel. So that's, and then technical features that are important here. Capturing packet loss and latency, which is going to affect navigation performance primarily, and also capturing the fact that the data we're sending is going to substantially affect the topside display, as well as the kinds of command and control messages that we can send down to the vehicle. So to capture all these features and to provide this hierarchical approach I mentioned, we developed 2 simulators. There's the vanilla NetSim, which is the hardware-in-the-loop simulation that tries to capture as many full oceanographic features as possible, such as that Beaufort lens effect, using a virtual ocean model which incorporates multipath, noise, surface interactions, refraction, etc. This uses the actual acoustic modem hardware minus the amplifiers and transducers, so you have the actual A to D, D to A, the firmware, serial interface, etc. It's a single user system, however, because you have all this hardware involved. So it was used for communication-specific development as well as for these virtual experiments when we tried to get everyone together and perform the experiment as if we were doing it for real. And then the other side of it is this low-fidelity simulator, NetSim UDP, which tried to capture at least the application interfaces to the comm system. So from the application, you see this the same way. The latencies using an accurate sound speed profile for the environment, and with somewhat correct packet losses, using a probabilistic model that's simplified from the real environment, but gives you realistic enough packet losses for most of the development needs. And this used UDP instead of actual micromodem packets. But the important thing here is that it runs on a laptop, no specialty hardware, and it was easy for all the developers to run every day as part of the rest of their system integration testing. And so we didn't suffer from the situation where no one actually ran the communication simulator because it was too difficult to run. But we did have a high fidelity one when we needed to for communications development as well as the virtual experiments. So graphically, you have NetSim on the left versus NetSim UDP on the right. The key thing here is just looking at how much less hardware, which is represented kind of by these boxes in the middle, are required for the NetSim UDP. But otherwise, the core simulation components are largely the same. And looking at a few results. So this is the full NetSim in the 30-meter transmit, shallow, and 100 meters deep transducers. And all these dots are receptions at a different depth and range. And you can see in the shallow case, you have the surface channel, and then you get the shadow zone out here. And then the deepest case, you end up losing some of the packets in the shallow, but having much better coverage across this overall space. And so we expect to see on average that shallow receivers perform better when the vehicle is shallow, which is this box here in blue, and I expect deep receivers to perform better when the vehicle is deep. So looking at the actual data from this experiment, we have the SNR out of the modem as well as the equalizer error, which is plotted with low error on the right, so these 2 curves are visually comparable. And in general, we see, with the exception of this particular dot, that shallow receivers, which is these X's, perform better than the deep receivers when the vehicle is shallow. This is vehicle depth along the y-axis. And then when the vehicle is deep, we see that the deep receivers, these little circles, perform better when the vehicle is deep in this below, say, 40-meter layer, which maps onto what we saw in simulation. It shows that the real data represents the same effect that we were seeing in the simulated data. It motivates some of the capturing of the underlying oceanographic features. So in conclusion, high latitude deployments involve significant logistical and technical challenges, as we know. And I think these technical challenges, and to some degree the logistical ones, can be largely met with careful application of the virtual ocean simulation. Because with simulation, you don't need to bring your team to the Arctic to develop and test large amounts of the system. And a tiered approach to simulators with a low fidelity but easy to use, and a high fidelity, harder to use but more robust and capturing more of the features that you need to know, as well as a clear separation between runtime and simulation components, which I think is very important to taking the work you've done against the virtual ocean and ensuring that it actually works when you go deploy it in the real world. If you want to see more about this project, there's a couple other papers that we've written on various aspects of the system. The documentation on NetSim itself is an open source project at this URL. And for access to the virtual ocean code, you can email the laboratory and we'll set you up. And I'd like to acknowledge everyone involved in this project. There are quite a few people that tangentially and directly helped us out with this project, as well as the video in this presentation. And with that, I'm happy to take any questions about this work. Thank you.